Okay, so like I was saying, this will be something that's very relaxing for you after an exam. This is just an analysis of some more features in the vibrational spectrum. We've covered the fundamentals, the fundamental vibrations. When we looked at your fluorobenzene, and you simulated those spectra and so on, those were the fundamentals. So all of the 0 to 1 transitions for every vibrational mode. So we didn't have any overtones, which would be like a V equals 0 going to V equals 2, so twice the vibrational frequency. And we didn't have any combination bands where you had multiple vibrations absorbing the photons at the same time. So I'm not exactly sure how conceptually to understand combination bands. I mean, we'll talk about it some more this morning, but in terms of their symmetry and what makes them allowed, we're going to look at the symmetry of the combination bands and overtones today. So what is a combination band or an overtone? Well, here's a simple spectrum: automobile exhaust. We have water in the exhaust. We have CO2. We've looked at these fundamentals. And so here's the fundamental for the bending motion. We see that P and R branch and the Q branch in the middle. So, we see the rho vibrational spectra here, the transitions. We have the asymmetric stretch for CO2. The symmetric stretch is Raman active only because it's a D infinity H molecule. It has an inversion center. We have water here. And then we have these peaks up here. And water is in this region. So this is water right here. Okay. But we have these other peaks that are pretty strong, and they show rho vibrational transitions. And so we know that they're a small gas phase molecule that actually is resolvable. So it's really small, meaning B values are big enough that we can see the separation of the rotational peaks. If B is too small, the spectrum just looks like this. We don't resolve the individual rotational peaks. But if B is big, then we see the individual P and R branches. Okay, I got kind of sloppy there, but you see how we can resolve the difference in the rotational lines because B is large enough compared to our spectral resolution. And so when we look down at these combination bands, we see that we can see individual rotational rho vibrational transitions. Well, also, if we were to look at the concentrations of the molecules, let's say we took the species that we have in this spectrum and we took individual spectra of each of those, and we changed the concentrations of those molecules, we would see that these combination band peaks grow and shrink with CO2. So they're CO2. Yeah. So, there's other things in here. There's water, there's carbon monoxide, maybe it's some complex or something like that. But no, if we look at carbon monoxide only, we don't see these. If we look at water only, we don't see those. So we put CO2 in the cell and these up here. So these are definitely CO2 vibrations. But what are they? Because we've got all three of the vibrational modes of CO2. Actually, there's 4, but this one's doubly degenerate. Okay, so this is an E mode and a A, G mode and an AU mode. So we've got all 4 vibrational motions for this triatomic molecule accounted for. And these are showing up as being related to CO2. But what are they? They're not pure fundamentals. They're combination bands. And so let's figure out what these frequencies are. So if we have these transitions in the D infinity H molecule, this A1U can interact with Z polarized light, A1G can interact with Z squared. These are the vibrations that we see. Okay, We can use the projection operator to give these different vibrational motions. Okay. And these combination bands are just what it sounds like, combination of these different fundamentals. So here's the IR active motion, 2300 wave numbers. Here's the Raman active, so we've got the 2-photon Raman effect. Okay, and that comes in at let's see, what was the frequency? The Raman mode was 1388. Okay. This down here, the infrared active nu2 motion, okay, was 700 wave numbers. And then this combination band, if we take 2 of this motion, so that's 700 plus 700, and then we add in nu3, which is 2300, okay, we get something that's close to 3684 wave numbers. Okay. So this is another way to write this would be 2 nu2 plus nu3. So that would be how we would designate that vibration. And the way you read it here, 2 nu3 plus nu3, is exactly what you would do to get the frequency of that. 2 nu2 plus nu3. And you just add those vibrational frequencies up, and that's the frequency of the combination band. Okay. Now, what are the symmetries? Well, we have the ground state symmetries here. That gives you all of these A1Gs. We can test it with Z-polarized light to see if that allows it, but we see it in the infrared, so we're pretty sure that that's what it is. And then we have nu1, okay, which is A1U here. And then we have 2 of the nu2 frequencies. And then we have no change in nu1. And so this is no change. So it really doesn't do anything to the problem because it's A1G, it's top row. Everything's going to be multiplied by 1s in that particular case. So we can look at the symmetries of these and see if this is, so this might be a hypothesis, right? This is one way to get to 3700 wave numbers. And so then we would go check the symmetry to see if that transition is actually allowed by symmetry. Okay. And so let's go ahead and look at that. So here's our light. Here's all of the symmetries that we put in. And we, of course, can combine all of those A1Gs into A1G. And then A1 times A1 gives A1. And then G times U gives U. We just do these pairwise. So A1 times A1 gives A1, and U times U gives G. Then anything times A1G is itself. Okay, so E1U times A1G is E1U. And so now it gets interesting. Okay. So whenever we combine the E's, E1 times E1 gives A1 plus A2 plus E1, and then the U times U gives G. Okay. So all of these are G because of the U times U. And then lastly, this A1 multiplied by each one of these terms individually gives us that set again. So A1G times A1G gives A1G. A1G times A2G gives that, and A1G times E1G gives that. But all we're really looking for is which one of these. We're just looking for that A1G. So when we see that, we know this is not equal to 0, and this is an allowed transition. Okay, pretty straightforward. The one downside of using the symmetry selection rules is what? Can you help me understand what's missing here? Why this is satisfying? We know that it's not equal to 0, but what's missing really?
The actual intensity.
Yeah. We don't know. Yeah, we don't know how different from 0 it is, right? We know it's non-zero, but it could still be a really weak transition. This is just saying it could show up in the infrared spectrum. We don't know if it's going to be strong enough to see, but it could show up.
The difference between possible and probable.
Yeah, so
we don't know if it's
yeah, and so it may be possible, but the probability may be really small. And so the intensity is really the probability of this transition occurring given photons at that energy. This integral is telling us what the probability of that transition happening. So a photon comes in with this energy, and if this is a big number, then it's highly probable that photon will be absorbed. Okay. If this is a really small integral result, the photon could match the energy, but it's just not very probable, so it goes right through. So not every photon is going to be absorbed, that hits a molecule that matches a symmetry selected or symmetry possible transition. Okay, so that's that 3684 band. This one is the 2 nu 2 plus nu 3. And can you see what, how it's being shown here with the parentheses? Yeah. And so that's kind of what's being done here on the x-axis. We're going from this is just showing you the Schrodinger equation here for the 3 vibrational modes, and here's the other Schrodinger equation for the 3 vibrational modes, and we're taking the differences in the excited states to the ground states. The ground states are all zeros, right? We're in the ground state, so that's the energy of the ground state, and these are the excited states, which can be simplified just to parentheses showing you the 3 excited states. And so that's what's being shown here. This results in the molecule being in the 0 or the ground state for nu 1, the second vibrational level for nu 2, and the first vibrational level for nu 3. So. Okay, let's look at the 3730 combination band. Oh, do we do that one? Just a minute. Okay, well, let's look at that one anyway. So here we have 3730. So here we have 2350, so that's nu 3, okay? And if we add in nu 1 at 1380, 0, 13, 6, 7, so 3730. So that matches, nu 1 and nu 3 matches this frequency right here, which again would be the middle frequency of that block of lines. Let's look at the symmetries. I think the rest of the notes, let me just make sure. I'm going to scroll fast forward. These are all acetonitrile, yeah. Okay, so let me keep those and go back. I just wanted to make sure I wasn't doing something that was later in the notes. Okay, so let's go ahead and do this one on the fly for 3730. So what is the symmetry of nu 1? Go back in the notes and let me know that. Symmetry for nu 1. It's A1G, okay.
A1U for...
Yeah, A1U for nu 3, okay. And then Z polarized light is A1U, right?
Yes.
And then the ground states, 0 and 0. I'll go ahead and write these out here. 1, 0, and 1. So we have all those A1Gs there. And again, when you take all those A1Gs times this A1U, you end up with A1U. And so then we're going to combine these. U times U is G, and A1 times A1 is A1, so A1G. And then we have all of these in there too, so that's going to give us A1G. So our last result, all of these are singly degenerate, so they're all A1s. And we've got this result times A1G again, times A1G again, so that's, again, not equal to 0. So this one is allowed as well with Z-polarized light. Okay. We add the frequencies, we get 3730, so that's the new 1, plus new 3 combination. Now you could think about all of this. You could make a bunch of different combinations. You could have A1 plus one of the new 3s, right? You could have new 1 plus new 3. You could have new 3 plus new 2. This one's strange. It's 2 new 2 plus new 3, right? I mean, think of all of the combinations you could come up with. And yet we don't see any of those other combinations in here. That doesn't mean they're not allowed by symmetry. It just means they're not probable, right? So we could come up with a whole lot of allowed combinations. It's the actual result of that integral that tells you if you're going to see it or not in the spectrum. If it's not allowed, you won't see it. If it is allowed, you may or may not see it. Okay, let's look at something that has slightly different symmetry. So here's acetonitrile. Oh. We looked at all of the vibrational modes in acetonitrile in a previous lecture, probably a month ago. And so let me go ahead and write out the structure. Okay, so how many vibrational modes do we have? 1, 2, 3, 4, 5, 6. So N equals 6. 3N equals 18. Yep, 18 minus 6 equals 12. And here's all the vibrational frequencies, and I only see 8.
Symmetry was we call that signal, right?
Well, 4 of them are degenerate.
Yeah, that's it.
That's what I'm saying.
Yeah, so these 4 right here count as 2. All right, so 1, 2, 3, 4, plus, 5, 6. We have 5, 6, 7, 8, 9, 10, and 11, 12. So there's all 12 vibrations in this molecule, and here are the frequencies. So these are all doubly degenerate. There's actually 2 vibrations going on here, 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 and here. So we should see 8 peaks in the spectrum, and here we have our spectrum, and it's got quite a few more peaks. Okay. This is an impurity, I know, because I did these, I did this spectrum myself, and I got some fresh out of the bottle one year, and it got a really good spectrum, and then I went back to that same bottle. It had been open, and some of the glue in the cap and all that had leaked down in there and everything, and I started seeing extra peaks in the spectrum. And so those peaks are garbage. They're dirt. They're glue from the cap. Yeah. And so then we end up with 1, 2, 3, 4, 5, and a shoulder, 6, 7, 8, 9, 10. Already we've got way more than 8 peaks in the spectrum. And so when we look up the assignment of this spectrum, we see that some of these are combination bands, like this new 3 plus new 4. Here's a new 7 plus new 8. Here's an overtone, 2 new 8. So what we might think is a pure motion is actually an overtone. And so that means that's twice the frequency. So way over here off scale is new 8. And so let's look at the support for some of these combinations and overtones. Okay, so let's look at this combination band, new 3 and new 4, new 7, new 8, and then the overtone 2, new 8. So let's look at the new 3 and new 4 combination. So this is a new 3 and new 4. Let's go back up here and look at here's new 3. New 3 is A1. And new 4 is A1. So these are going to be all A1s, and the combination is A1 as well. So we have the ground states are A1 and A1. Light, Z-polarized light is A1, and the excited states are A1. So everything is A1 all the way down. And that's the top row. And so that's not equal to 0. So we know this one is allowed because everything was fully symmetric. Okay, if I go too fast, you can check the video just to make sure your work is right. But this one's pretty straightforward. So let's go on to the next one, the 7 and 8. So let's go back to our spectrum here. Actually, let's go back to the table here. New 8 is E, okay, and 7 is E, okay, and XY polarized light is going to be E, okay. So let's look at that one. So again, the ground states are fully symmetric. These guys here are top row. Z polarized light is top row, and the new 7 and new 8 are E. So is everybody capable of filling that part out? Okay. Do these pairwise. These first 3 are pretty easy. We get out on an A1, and then A1 times E is E, and then we have E times E. It's going to give A1 plus A2 plus E. So we go to our direct product table. Yep, and we see that E coming down and combining with E. So we get this full set. All right, and so again, think about this as an integral. That's what these things represent. And so now we have an integral that's the sum of 3 terms, and one of those terms is non-zero, that A1 term. And so this is allowed with Z-polarized light. And because we don't have G's or U's or whatever, it's probably going to be allowed with XY polarized light as well. So let's look at XY polarized light. So now in between, our operator is no longer A1, our operator here is E. But we're going to have 3 E's times each other. So this cranks up the difficulty just a hair. And so we have A1 times A1 equals A1. A1 times E equals E. We go to the direct product table. We see that that's the set of A1, A2, and E. And just like algebra, you just multiply this E through. So we're going to have E times A1, E times A2, and E times E. So E times A1, that's this one. So that's an E. E times A2 is this one, and that's an E. So that's where these 2 of these 3 E's came from, and then E times E is this whole thing. And so we end up with that result, and we have A1, so it's non-zero. Okay. So again, the symmetry selection rules are very easy. The math associated with this would be disastrous. I don't know how. Yeah. I mean, just the one-dimensional particle in a box took 6 or 7 pages of algebra and calculus. And so this is really saving us a lot of time to determine if it's allowed or not. Okay. Let's go ahead and do the combination, or the overtone. So the overtone was 2 nu 8. And again, that 2 nu 8 is going to be E here. It's actually, we don't have to do it. It's going to be this one right here. again, the 2 nu 8 is going to have 2 E's, and it's going to be allowed as well. So that's all I've got for today. This was a really short lecture. What I have got for next time is the rotational selection rules by symmetry. Okay, I can start that one now, so I can go a little slower. It requires what do I want to say? It's not exactly straightforward in terms of following the character table and the direct product table. So let me go ahead and start that. And so you may not have the notes in front of me, but that's okay. Don't be bothered by that. So I'm going to stop this.